Welcome back. Today we will take our first look at induction, and this starts a new topic, and the topics within this module will include mathematical induction, strong induction, and then a look at some recursive definitions and structural induction. So the first topic then is mathematical induction. So this topic can be broken down into three different pieces. We'll first look at the principle of mathematical induction, then we'll go through several examples of proof using induction, and we'll end with guidelines for proof that make use of induction. So what's the big idea behind induction and when would we make use of it? The idea is that sometimes we want to prove things over an infinite domain. So that is, we want to start at some base and just keep on going. So over all the integers greater than 0, or over all the integers greater than or equal to 4, whatever that is, if that domain is infinite, proving this doesn't work by looking at each and every element in the domain and proving it for each of those elements. So sometimes we have to take a different approach. And you can think of this as showing that you can climb an infinite ladder. And we wouldn't have time to watch you actually climb that infinite ladder, but you could prove to us that you could if you could show us that you could reach that first rung. So that's the first hurdle. Can you reach the first rung? And the second step is, if I reach any rung k, can you show me that that proves that you can reach the next rung, rung k plus 1? If you can do that, then while it would take you an infinitely long time, then I know, assuming you're not too afraid of heights, that you can reach the top of this ladder, or you could keep going. And so what that looks like in terms of mathematical proof is you're showing that reaching that first rung is showing the predicate is true for n equals b. So if we have some predicate p of n, you're showing me that you can reach the first rung. You can reach p of b. And that next piece, if we can reach rung k, then we can reach rung k plus 1. You're saying that for any arbitrary k, p of k implies p of k plus 1. Put that together, and what we have is the fact that over all n, all integers n greater than or equal to b, p of n holds. And that's what we want to show with induction. The principle of mathematical induction is this: to prove that for all n in z greater than or equal to b, i.e., so this is saying that we want to show that p of n is true for all integers n greater than or equal to b. What we want to do is first show the basis step, and that is to show that this is true when n is equal to b. So whatever that lowest integer is that we want this to hold for, we want to show that is true. So this is showing that we can reach that first rung of the ladder. So if it starts 4 feet, 6 feet off the ground, we want to first show that we can reach that first rung, and then the second step, the inductive step, is to show that if we get to the ladder, we can keep climbing. So if p of k is true, that implies that p of k plus 1 is true. If we can reach rung k, we can reach rung k plus 1. And we want to show that that's true for all integers k greater than or equal to b. And what that gives us, if we show it's true for the base, then it's base b, that first rung is b, then it's true for b plus 1. If it's true for b plus 1, that implies it's true for b plus 2. And so together, that shows us that we can get to the top of the ladder, even if we never do. All right, so the first step is just showing that this is true. So we just let n equal b, and we show that that's the case. The inductive step is sometimes the trickier bit, and that is where we have to show an implication, where if we assume that p of k is true, this implies that p of k plus 1 is also true, and for all of those integers k greater than or equal to b. And so we do this by first making our assumption. Our assumption is that this is true when n is equal to k. So P of k is true. We assume that. That's our inductive hypothesis. So this inductive hypothesis is what's going to help us show that the rest follows. So from that, we want to show that if P of k is true, then P of k plus 1 is also true. Let's take a look at some examples. So as a first example, we'll take a look at a summation, and that is the sum of the numbers 1 to n. And before you try to prove anything, you're going to want to have some motivation. So maybe some smaller examples that make you believe that this is likely the case. So you create a conjecture based on evidence, and maybe you look at the sum of the numbers 1 and 2, then 1 through 3, then 1 through 4. But as a motivation to show that this is true, I'm going to go to an example that is a common one, and that is the sum of the numbers 1 to 100. Let's let S be the sum of 1 plus 2 plus 3 all the way up to 100. And the story goes that one young mathematician, Carl Friedrich Gauss, was in school one day, and the teacher wanted to give the students a task that would take them a long time. And so the task was to sum the numbers 1 to 100, and thought that it would take a fair bit of time and set the students forth. And Carl Gauss, a young boy, came up with the number 5,050 very quickly. And the teacher thought, well, that must be cheating, and asked him to explain what had happened and how he got to that answer so quickly. And the reality is he just came up with a really clever way to find this sum. And he noted that if you add the numbers forward, it's the same as adding the numbers backward. So if you add both of those together, you get twice the sum is equal to 101 plus 101 plus 101, all the way up to that last set. And because you can see there were 100 terms, that means that this is the same as saying twice the sum is equal to 100 times 101. Each of those 100 terms added up to 101. And so the sum was 100 times 101 divided by 2. And you can see how that fits in. This is n, in this case, is 100, and we're getting 100 times 101 divided by 2. So that's a motivation, but let's start. And so what we're trying to show is right up here. P of n is the sum of the first n digits is equal to n times n plus 1 over 2. So the basis step is showing that P of 1 is true, because we want this for n equals 1, 2, 3, 4, 5. So our base in this case is n equals 1. So we want to show that P of 1 is true, and that is the sum of the first 1 digits is equal to 1 times 1 plus 1 divided by 2. We can do that because that sum, that's just 1, and that's equal to 1 times 2 over 2, which is the same as 1 times 1 plus 1 all over 2. And that's it. That's our basis step. Done. So then we have to figure out, well, what is the inductive step? What's our inductive hypothesis? This is where we assume that P of k is true. So we're going to assume that the sum of the first k digits, so 1 plus 2 plus all the way up to k, is equal to k times k plus 1 over 2. So from that, we then decide what we want to show. And what we want to show is that, and this is where it ends. So we start green and we end on red. We must show that P of k plus 1 follows under that inductive hypothesis. So we know we can assume that first piece is true, and now we have to show that the sum of the first k plus 1 digits is is equal to k plus 1 times k plus 1 plus 1 all over 2. And we can see that's the same as saying k plus 1 times k plus 2 all over 2. All right, so how do we start that? Well, the sum of those first k plus 1 digits, I equals 1 to k plus 1, is just 1 plus 2 plus plus k plus 1. But this here, that's what we know from our inductive hypothesis. So this is equal to k times k plus 1 over 2 plus k plus 1. And this is by our inductive hypothesis, by IH. Well, what can we do with that? We want to get that k plus 1 inside, and so what we can do is we can say, okay, well I can just do some basic math. K times k plus 1 over 2 is equal to, I want to put k plus 1 over 2, so it's 2 times k plus 1 over 2. Now I can add these two together. Oops, that should be a plus. There we go. And now I can add them, I can put them over that same denominator. So I've got k times k plus 1 plus 2 times k plus 1 all over 2. And I can pull that together, right? So I see that I've got k plus 1 as a common factor, so this all becomes k plus 2 times k plus 1 all over 2. And while the order is different, we know that that's the same as k plus 1 times k plus 2 over 2. And that's the end of our proof. We've shown that if p of k is true, then p of k plus 1 must follow. Here's another example, and this is the sum of the first n odd numbers is n squared. And this might be something that you hadn't seen before, but if we add up the first 1 odd numbers, well, that adds to 1. 1 plus 3, the first 2 odd numbers, is 4. 1 plus 3 plus 5, the first 3 odd numbers, is 9. 1 plus 3 plus 5 plus 7, the first 4 odd numbers, is 16. Or alternatively, 1 squared, 2 squared, 3 squared, 4 squared. And this continues. So you might say to yourself, well, that's cute, but does it hold for all? Is this true for all n in z greater than 0? Is this always true? To show that it's true, I can't list off every example, but I can prove it by induction. So the first question we might have is, what does this mean to be the sum of the first n odd numbers? What is the nth odd number? I can list out and find the fourth one, but let's look at them in order. 1, 3, 5, 7. What is the kth number? The k plus first number. What is the nth number? So the first number is 1, and I can represent that as 2 minus 1. 3 is 4 minus 1. 5 is 6 minus 1. And 7 is 8 minus 1. And if I follow through, what would that look like for k? Well, I can show you that this is the same as 2 times 1 minus 1, 2 times 2 minus 1, 2 times 3 minus 1. This is just another way to represent all of those odd numbers, 2 times 4 minus 1, and so on. And what that means for us is that the kth odd number is equal to 2 times k minus 1, and the k plus first odd number is equal to 2 times k plus 1 minus 1. And we're going to need that. So the nth is 2n minus 1. So making use of that then, this sets up what we want to prove in terms of p of n. So our predicate then says, I want all the odds, 1, 3, 5, all the way up to 2n minus 1. If I sum those together, I'm going to get n squared. So our basis step is just to show that p of 1 is true. P of 1 is just showing that 1 plus no other odd is equal to 1 squared. I'm going to say I believe that one. Even stating it almost shows that it's true. 1 is equal to 1 squared. Okay. So the inductive hypothesis is to then assume that this is true for n equals k, when k is greater than or equal to 1. So we're going to assume that 1 plus 3 all the way up to that kth odd number, 2k minus 1, is equal to k squared. Great. What we need to show is that p of k plus 1 follows. So if I add on that next term, then this sum becomes k plus 1 squared. So, and I think it's important with sums that we see that generally what we do when we're looking at p of k plus 1 is we're just getting one extra term. What we want to show then is that this sum, 1 plus 3 plus 5, all the way out past that kth odd number, 2k minus 1, all the way out to the k plus first odd number, which is 2 times k plus 1 minus 1, or 2k plus 1, is equal to k plus 1 all squared. Okay, but we know that this first bit, that is exactly what we're given by p of k. And so this is just equal to k squared plus 2k plus 1 by that inductive hypothesis. And then we can see that this is equal to k plus 1 times k plus 1, which is equal to k plus 1 squared. So this is everything that we need. And so we conclude that by induction, the sum of the first n odd integers is n squared. And then you put your stamp of approval at the end of your proof. Okay, so let's take a look at another example where we look at inequalities. And so here's an inequality that holds for n in z greater than or equal to 4. So if we think about our ladder to the sky, what this means is that if this is heading up into a tree house at the top, what this means is this first rung is at 4, and you start climbing from there. So if you're a little kid, you're not going to be able to reach it. If you can only reach up to 1 or 2, you may not reach this ladder. So we have to show that if you can climb this ladder, you are able to reach a rung that starts at 4. So our first rung in this case, and our base case, is to show p of 4. All right, so that's our basis step. So our approach, we want to show that this is true for all n in z greater than or equal to 4. And so our basis step is to show that p of 4 is true. And that's showing 2 to the 4th is less than 4 factorial. So we want to show that for all n greater than or equal to 4, 2 to the n is less than n factorial. But we have to start by showing that we can reach the first rung of the ladder, and that we do by showing that 2 to the 4th is less than 4 factorial. And I can do that by showing that 2 to the 4th, I know what that's equal to. That's 2 times 2 times 2 times 2, or 4 times 4, which is 16. and that is less than 24, which I happen to know is 4 factorial, 4 times 3 times 2. And that's all I need to show my basis step. That base case is covered. So the next step I have is the inductive step. And in this inductive step, I first have to determine what is my inductive hypothesis. So what does this look like if I assume that this holds for n equals k? So this is assuming that for some k, for some k greater than or equal to 4. So it's starting from that base case and onward. It has to be within the domain. For any k within the domain, I'm going to assume that 2 to the k is less than k factorial. And then from that, I want to show that p of k plus 1 follows. Assuming that 2 to the k is less than k factorial, can I then show that 2 to the k plus 1 is less than k plus 1 factorial? So this is more straightforward than you might think, and that is we have 2 to the k plus 1. I know that this is equal to 2 times 2 to the k, and I want to get it in terms that I feel happy playing with. I have assumptions around 2 to the k and k factorial and how they're related. So if I can get to a point where I see 2 to the k in my terms, I know I have an assumption that I can work with. So I see that this is equal to 2 times 2 to the k, just by definition of exponents. But this is less than 2 times k factorial by my inductive hypothesis. So what can I do with that? Because I don't know how to play with 2 times k factorial, but I do want to get to k plus 1 times k factorial. And I know that k is greater than or equal to 4. So I know that k plus 1 is greater than or equal to 5. So I can do the following. I can say, well, that is less than k plus 1 times k factorial because 2 is strictly less than 5, which is less than or equal to k plus 1, because k is greater than or equal to 4. So k plus 1 is greater than or equal to 5. Well, this is k plus 1 factorial. And that's all I need to show, that for all n in z greater than or equal to 4, 2 to the n is less than n factorial by induction. So that last step is just concluding our proof. And then we stick our Helmholtz symbol or something to denote we've reached the end of our proof, and we can drop the mic. All right. The last example is that of divisibility. And here we're going to show that for all positive integers, n cubed minus n is divisible by 3. So first of all, you have to convince yourself, is this so? We generally look to examples first and then decide if this makes sense and is worth exploring. So you can check that we'll start with n equals 1. Newsflash, this is also our basis step. When n equals 1, then 1 cubed minus 1 is 0. And 0 is divisible by 3 because this is 3 times 0. N equals 2. This is 2 cubed minus 2. Our n cubed minus n is 2 cubed minus 2 in this case. But that's the same as 8 minus 2, which is 6. Or this is 3 times 2. So this is divisible by 3. How about n equals 3? 3 cubed minus 3 is the same as 27 minus 3, which is 24. Or you can represent that as 3 times 8. And you could try other examples, but maybe that's enough to help you see that you believe it will be true. So here's our basis step, we'll just remember that that exists. And we'll see that what we want to show, P of n is saying that n cubed minus n is divisible by 3. Another way of saying that is that n cubed minus n is equal to 3 times some integer. And that's what we were showing on the previous page. So in fact, we've already shown our basis step. We've shown that 1 cubed minus 1 is divisible by 3. And that's because 1 cubed minus 1 we showed was 0, which is 3 times 0. And 0 is an integer. And so that means that this is evenly divisible by 3. Okay, so what's our inductive step? First, we have to assume an inductive hypothesis. Our assumption is that P of k is true, that k cubed minus k is divisible by 3. Another way that we can think about that is that k cubed minus k is equal to 3p for some integer p. We don't know what it is, and we don't care, but we know that if it's divisible by 3, then I can find an integer such that k cubed minus k is equal to 3p. So we want to show then that p of k plus 1 follows, that if I put k plus 1 in for n, I will still get a result that is divisible by 3. So that is k plus 1 cubed minus k plus 1 is divisible by 3. To show this, we're going to have to find a way to get back this term and then know that that piece is divisible. So let's play with this. And that is k plus 1 cubed minus k plus 1. But this is just equal to, let's separate this out, and we see that if we take k plus 1 and cube it, what we get is k cubed plus 3k squared plus 3k plus 1 minus k plus 1. So minus k minus 1. Okay, so we still don't have anything that looks quite right yet. But what I do see is that I've got a k cubed and I've got a minus k. And so I'm going to move those two around. And I'm going to pull those together. So I get k cubed minus k. And then I still have these remaining terms left over. Plus 3k squared plus 3k plus 1 minus 1. Well, I can see the plus 1 and the minus 1 are going to go away. But let's work with that again. So now I've got this piece that I want to keep to the side that I feel pretty good about, plus 3k squared plus 3k, because these have canceled each other out. So then by inductive hypothesis, I know that there is some value, integer value p, such that k cubed minus k is equal to 3p. So I end up with something of this form by our inductive hypothesis. And what that means is I can pull a 3 out and I get something of the form p plus k squared plus k times 3. And that means that this is divisible by 3. Therefore, by induction, for all positive integers n cubed minus n is divisible by 3. So that's it. What are the guidelines that we want to follow so that we can successfully reach the end of an induction proof? First of all, we have to be able to express the statement that we wish to prove clearly. And this will be in the form something like, for all integers n greater than or equal to b, some predicate based on n holds. So p of n is true. And then we're going to write out basis step. We're going to actually write out the words basis step. Then we're going to show that our base case, this b, is true, taking care that we use the correct value of b. That's important. What is the first rung of the ladder that we have to reach in order to climb? Following this, we will write out the words inductive step. And then we're going to state our inductive hypothesis in the form, assume that P of k is true for an arbitrary fixed integer k greater than or equal to b. Now we need to know what we want to show. So state what needs to be proved under the assumption of that inductive hypothesis. So assuming that P of k is true, write out what P of k plus 1 says. That's what we want to show. Finally, we need to prove this. And we prove this statement, P of k plus 1, most importantly, making use of that assumption that P of k holds. This is important. And generally, the clue as to where you want to go is the direction that will take you in a path that will allow you to use what you know about P of k. So you want to make sure that your proof is valid for all the integers in that domain of interest. So all those integers k greater than or equal to your base case b. Most importantly, thinking about small k and especially k equals b. Make sure that you're not assuming that k is very large. And the final wrap up that seals the deal on this proof is you conclude that that inductive step is finished. This completes the inductive step, and end with, by induction or by mathematical induction, P of n is true, whatever that reads to be, for all integers n, where n is greater than or equal to your base step b. And that's it. Induction in a nutshell.
That was fun. What comes next?
Next up, strong induction. Thanks for watching.
See you next time.